All right, so let's talk about the exercises from the checkpoint for Module 8. So first thing we're asked is, so we're given a couple of conditions here, and we're asked which of the following might be false. So we're told that f is continuous over some closed interval and differentiable for some open interval, so same endpoints. So which of the following could be false? So part A here, or choice A, this is the conclusion of the mean value theorem. So basically, this is the instantaneous rate of change at a single point, and this expression on the right of the equal sign is the average rate of change over the entire interval. So this is a guarantee that comes from having a function that's continuous over a closed interval and differentiable over the same open interval. So we can throw this one out. What about B? So f prime of c equals 0 for some c. So basically what that's saying is this: if I have a function that's continuous and differentiable over the appropriate intervals, then there has to be somewhere where the derivative is equal to 0. So what if I have a function that's just a straight line? So a straight line is continuous and differentiable over whatever interval I want it to be. But at no point will the slope of this straight line be 0. So because of that, I can say that B might not be true. It might be false. Next, question 2. So we have a function. We're given the derivative of a function, and it is known that f of 1 is 7, f of 5 is 11. From there, we are asked what value of x in this open interval satisfies the conclusion of the mean value theorem. So it sounds like we're already assuming the mean value theorem was satisfied. Why is that a safe assumption? So we are told that this function's derivative is given by this expression for any positive x. If the derivative exists for any positive x, that means the function's differentiable for any positive x. And if you have a function that's differentiable, it can't be differentiable unless it is also continuous. So that right there, that tells me that my function is continuous and differentiable over all positive x, and that includes these intervals 1 through 5. The mean value theorem has to hold. So now that we know that, let's find the average rate of change over this interval, 1, 5. So f of 5 minus f of 1 over 5 minus 1, that's equal to 11 minus 7 over 5 minus 1. So I get, all told, an average rate of change of 1. So the conclusion of the mean value theorem is that there has to be some value of c on this interval such that the derivative is equal to 1. So I'm going to take my expression for the derivative, 2c squared minus 5 over c squared, that equals 1. I'm going to clear the fraction by multiplying by c squared. So I get 2c squared minus 5 equals c squared. If I continue to solve, what do I get? I get negative c squared equals negative 5 over c squared equals 5. So taking the square root of both sides, so I get c equals plus or minus square root of 5. So only one of these, two solutions here, only one of these is on the closed interval. It has to be the positive one. So my final answer here is c equals radical 5. Right, moving on to question 3. Hot water is dripping through a coffee maker, filling a cup of coffee. So the amount of coffee in the cup is given by this differentiable function where t is measured in minutes. So selected values, so t stands for how many minutes have passed since I started filling this cup of coffee. C of t stands for the number of ounces of coffee in the cup as a function of time. So what I'm being asked is there a time on this subinterval T4 such that C prime of t equals 2? So it might be tempting to, jump straight to the average rate of change and say, oh, the average rate of change. Well, let's do that first. What is the average rate of change of that interval? So what is C of 4 minus C of 2 over 4 minus 2? From the table, C of 4 is equal to 12.8. C of 2 is equal to 8.8. So I get not 4 minus 2. So this comes out to be 4 over 2, which is 2. So my average rate of change is 2. It might be tempting to say, all right, then yes, the mean value theorem says that there has to be some place over that interval where the average rate of change is equal to the instantaneous rate of change. We should probably make sure, though, can we say this function is continuous and differentiable? Well, if we think about the context here, as we're filling up a coffee cup, will that be a continuous function? Let's look at it this way. Can we ever have discontinuities? If I'm filling up a vessel, a cup full of coffee, is it possible to have a discontinuity in it? Can I just jump like that? Hopefully, I can convince you that's impossible. So I can't be filling up a cup of coffee and then that jumps. The amount of liquid in the coffee just like abruptly jumps from one value to another without passing through the values between those two things. That's also going to be true of the derivative. So because of that, I can say yes. Because this function I'm thinking about here is continuous and differentiable, I have to be able to. I have to have a point where the mean value theorem is upheld. All right, next we're looking at implicit differentiation problem. So we want to find the value of dy dx at a specific value of x. So I'm going to use implicit differentiation because I don't have an explicit expression for y in terms of x. Like I have my variables kind of jumbled together. So because of that, yeah, let's do implicit differentiation term by term. So I'm going to differentiate each one of these terms with respect to x. So 3x squared, that becomes 6x. Negative 2xy, I have to use that product rule there. So I'm going to break this down into the functions negative 2x and positive y. So if I do that, what do I get here? The derivative of negative 2x is negative 2y. So derivative of negative 2x times y. Then I'm going to add to that minus 2x times the derivative of y with respect to x. So that'll be minus 2x dy dx. And then what's the derivative of y squared with respect to x? Well, I got to use chain rule there. So that'll be 2y for the outer part of the chain rule, and then dy dx, because I'm differentiating y with respect to x. And then on the right-hand side of the equal sign, I have 2. The derivative of 2 is 0 because it's a constant. So now I want to find so we've done the differentiation, but we want to solve for dy dx at a given x value. So there's a lot of ways to approach this from here. What I'm going to do is this. I'm going to substitute 1 in for x. So 6 times 1 is 6 minus 2y minus 2 times dy dx plus 2y times dy dx equals 0. And now I'm going to start moving things around because I want to solve for dy dx. Actually, I can go a little further here. So I did not substitute anything in for y, but what I can do is this. I can go back to the original equation and plug in 1 for x and see what my y value is. So off to the side here, 3 times 1 squared minus 2 times 1 times y plus y squared equals 2. So 3 minus 2y plus y squared equals 2. So I get y squared minus 2y plus 1 equals 0. I believe that factors. And it factors into y minus 1 times y minus 1 equals 0. So I get y equals 1. So when x equals 1, y equals 1. So I can make that substitution as well. 6 minus 2 times 1 minus 2 times dy dx plus 2 dy dx equals 0. And this is a problem. It looks like my dy dx's are going to cancel. Is that supposed to happen? So let's look at it from the beginning. 6x minus 2 times y. That looks good. Minus 2x times dy dx plus 2y dy dx equals 0. Okay. I plugged in 1 for x. So 6 minus 2y minus 2 dy dx plus 2y dy dx equals 0. Okay. So I believe this over here. 3 times 1 minus 2 times 1 times y plus y squared equals 2. So 3 minus 2y plus y squared equals 2. Y squared minus 2y plus 1 equals 0. Does this factor out correctly? Y squared minus, yeah, it does. All right, forgive the choppy edit here, but so I have confirmed that what happens here is after these derivatives cancel, I end up having 6 minus 2 equals 0, which is clearly nonsense. So what we have here is that dy dx is undefined. We were unable to come up with a real solution for that. Moving on to question 5. I want to find the derivative of the arc sine of 2x. So we can apply chain rule here and rely on an inverse trig relationship that we have used. So we know that the derivative of arc sine of x is equal to 1 over 1 minus, oh no, not quite, 1 over the square root of 1 minus x squared. So what changes when I have the arc sine of 2x here? So what's the derivative of arc sine of something? The derivative of arc sine of something is 1 over the square root of 1 minus that something squared. So basically, I'm using the chain rule here. I'm taking the derivative of arc sine of 2x with respect to 2x first. So that's why I'm leaving this 2x intact. So that's the outer layer of the chain rule. The inner layer requires me to multiply this by the derivative of the inside function, which is 2x. The derivative of that is 2. So what I have here now is 2 over, I'm going to simplify what's inside the radical a bit, 2 over 1 minus 4x squared. So that should be complete derivative for the arc sine of 2x.